Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 17, Vectors and Matrices in Higher Dimensions. As it happens, everything you learned about in the previous video can be generalized to 3, 4, and even higher dimensions. In this video, everything from the last video will be restated in a three-dimensional context. The generalization to 4 dimensions follows the same algebraic pattern, and as it happens, 4-dimensional vectors and matrices are used all the time in computer graphics for reasons we'll discuss in a future video. To begin, 3-dimensional space is usually visualized with 3-dimensional axes, x, y, and z. In OpenGL, the axes are oriented so that the plane spanned by the x and y axes aligns with a window that's used to display graphics. The positive z-axis you should think of as coming out of the screen directly at you, the viewer. Now, although these three axes are supposed to be perpendicular to each other, because of the way they're drawn with perspective, when projected onto a plane, this z-axis might not appear to be at a right angle. So I often find it helps to visualize the x, y, and z axes as being the back edges of a cube in three-dimensional space. And so these axes, being drawn with dotted lines, are being hidden from view. And that might help you orient yourself in this space. So each of the notations and operations generalizes pretty straightforwardly to 3 dimensions. Point and vector notation will still enclose points with parentheses and will still enclose vectors with angle brackets. And we'll often use subscripts so we don't run out of letters very easily. Sometimes for context, we'll write the components as x, y, and z. And when we move on to 4 dimensions, we'll call that fourth component W usually. But we'll see that in a future video. The operation of vector addition is very similar. To add 2 vectors together, you add them component by component. To do scalar multiplication, again, we do exactly the same thing as before. We multiply each component of a vector by whatever that constant number is. Once again, working with basis vectors will be very helpful. In 3 dimensions, the basis vectors are usually written as I, j, and k, and each one has 3 components. So I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. And just like it was the case in 2 dimensions, every vector in 3-dimensional space can be written in exactly one way as a combination of these basis vectors. And to see how that works, it's a very similar derivation. You could take x, y, z, and you could write that as the sum of 3 different vectors. Then from each one of these vectors, you could factor out a constant. So factor out the x, factor out the y, and factor out the z. And then these vectors that you're left with, well, those are I, j, and k. Your basis vectors in 3-dimensional space. Again, the reason we're really interested in basis vectors relates to linear functions. Linear functions, the definition is actually the same in any dimension because the definition actually has nothing to do with the number of components of a vector. Basically, a vector function is linear if it interacts well with scalar multiplication and vector addition. In other words, if you have f is a linear function, if you have a constant times a vector, then you can factor out that constant. If you have f applied to a sum of vectors, that's equal to the sum of f applied to each vector. Any function meeting those properties, satisfying those equations, is called a linear function, or sometimes a linear transformation. Now, the great thing about linear functions is, once again, you can actually calculate a linear function if you know the values of the function at each of the basis vectors. And that will help us write it in matrix form. Every linear function f of x, y, z, we're going to be able to write it in this form. And so some constants times each of x, y, and z, and those are added up for each component of the result. Every linear function on three-dimensional space has this form. And just like as was the case with 2 dimensions, it helps to think of these values, the different subscripted a values, as a discrete unit or an object. So they're grouped into a matrix. And then, so here are the constants. This group, this matrix of constants, times this vector is defined to be this result here. And you can multiply a matrix times a vector. As before, you can also multiply a matrix times a matrix. That naturally arises when you want to compose 2 linear functions. And again, it's easiest to think about this if we use the dot product. In 3 dimensions, v dot w, you calculate that by taking the product of each pair of components and then adding together the results. Right, so the dot product, the result, is a single number. And then the easy way to remember matrix multiplication of A times B is to partition A into row vectors, and to partition B into column vectors, and then use the dot product. And if you want to know the entry in row A, or let's say in row 1 in column 2, right, the entry in row 1, column 2 of the product is equal to the dot product of row 1 vector from the first matrix and column 2 from the second matrix. If you want to know the value in this location, right, this is in row 2 and column 3, the value in this position is the dot product of row vector 2 and column vector 3. And that's an easy way to remember matrix multiplication. Again, it's the similar kind of calculations in 4 dimensions. I won't really spend any time writing them out, just know that it works very similarly. As you might notice, these calculations can get tedious after a while. So in later videos, when we start to implement matrix-based transformations, we will be using a Python package called NumPy to do a lot of the calculations. But before we can use that package, we're going to have to learn how we can actually do the different geometric transformations that we're interested in. So we'd like to know how to translate vectors, how to rotate vectors, how to scale vectors, and how to do a perspective projection transformation to make objects far away from the camera appear smaller and objects closer to the camera appear larger. And as it happens, we can represent all of those different transformations using matrices. And that's why matrices are going to be so important. In the next video, we'll start to learn how those different types of transformations can be represented using matrix multiplication. Thanks for listening.